Welcome to the 9.3 video. In this video, we're going to talk about how to create hypothesis tests for means. This is going to be kind of similar to what we did to create confidence intervals for means in section 8.3, but now we'll talk about how to do a hypothesis test. So let's look at an example. In an earlier example, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that a regular AAA battery lasts for 30 hours of continuous use on average. A simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 8.9 hours. Do these data give convincing evidence that the new batteries last longer on average? So for hypothesis tests, again, we start by writing our hypotheses and then defining the parameter. So in this example, we would assume that the batteries are no different than typical AAA batteries and that they last on average 30 hours. So we would say h sub 0 has mu equal 30. But we're hoping to show that they actually last longer than 30 hours, that the alternative should be mu is greater than 30, where mu is the true mean lifetime of these new deluxe AAA batteries. So that's how we would set up kind of our first step. Let's continue. Our second step of completing a significance test is to check our conditions. So these conditions are going to be the same as doing a confidence interval for means. We're going to check the random condition, we're going to check the 10% condition, and we're going to check the normal/large samples condition, which we either can show by showing that our sample size is greater than or equal to 30, or we can use a graph or information about the data to show that it'll work regardless of any small sample sizes, just like for confidence intervals. Okay, now let's talk about how we can actually find our p-value and finish our hypothesis test. So just like we did in 8.2 where we said, 8.3, you can do this by hand, but we're really not going to worry about that. We're going to do the same thing for hypothesis tests. I'll show you the formula later on, but we're going to focus on being able to do these using a calculator rather than by hand. So if you want to do a hypothesis test for a mean by hand, again, you're going to start by going to stat, over to test, and then you're going to be looking for a t-test. That's the type of test we use for means, which is the second option. When you do one of these, you have an option, just like for confidence intervals, to either input your data as a list or as statistics. So if you choose statistics as the input, you'll need to give the mean, the stated value that you're testing. For our battery example, that would be 30 hours. That's the assumed baseline. Then you would give your sample mean. In our case, I believe it was 33.9 hours was the sample they found, the sample standard deviation, and the sample size. You would put that in, select what type of test you were doing based on your alternative hypothesis, and then calculate to find your p-value and then conclude. If you're given your information as data, you will still put in mu sub 0, the stated value you're testing, that 30 hours in this case, and then you would enter your data into L1 and select the type of test you were looking for and calculate. In our example, if we plugged in our information into a calculator and we got a p-value of 0.072, we would want to conclude, and that would depend on alpha, right? So if we had decided that alpha was 0.05, the p-value, we would conclude with a sentence like this: because the p-value is 0.072, we fail to reject the null hypothesis. There is not significant evidence that the new batteries last longer than traditional batteries. This is the type of conclusion sentence we want to see for hypothesis testing. In fact, it's actually two sentences. The first sentence will state the p-value and determine whether you're going to fail to reject or reject the null. Then you will talk about if there either is or isn't evidence for what we saw here. So in this case, there wasn't evidence that the new batteries last longer because our p-value is pretty big. Okay, so if you were to do this by hand, this is the formula that you would use. You would find your p-value using a t-value, which is a slightly varied version of a z-score formula again. So you'd have your sample mean minus mu over your sample standard deviation divided by square root of n, and you would use this. And then here is what the graph would look like based on your null hypothesis or your alternative hypothesis. Again, we're going to let our calculator deal with this. And again, you see the formula for a hypothesis test and a confidence interval that you can use. We'll talk more about using these potentially for multiple choice questions when we do some test prep at the end of the year. But as far as completing FRQs and things like that, you're going to be more concerned with using your calculator correctly. We've talked about two-sided tests that if you're doing them by hand, you need to double them, and the relationship to a 95% confidence interval. Yep. Okay, I think we're good to go. I think we've talked about all of this. Okay, so one thing that you can do with a hypothesis test for means that you can't do with a proportion is study what's called paired data. So we see this in comparative studies. So comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Studies designs that involve making two observations on the same individual or one observation on each of two similar individuals result in paired data. When paired data results from measuring the same quantitative variable twice, as in job satisfaction studies, we can make comparisons by analyzing the difference in each pair. If conditions for inference are met, we can use a one-sample t procedure to perform the inference about the mean difference. These methods are sometimes called paired t procedures. So basically, if I do a study and I take a data point on you at the beginning and at the end, and then I find the difference between the two, I can use the same strategies that we already showed you in this video on the differences. So think about, this could be really common in any sort of like weight loss situation. What's your weight before? What's your weight after the workout program or diet plan? Find the difference, and then you could study the differences just like normal data. We're going to look at some more information next. Okay, so here's an example. It says researchers designed an experiment to study the effects of caffeine withdrawal. They recruit 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which subjects took the caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers want to know if being deprived of caffeine would lead to an increase in depression. So we're going to be able to use those two sets of data to design and set up a paired data situation, which we'll see on the next slide. So here we can see each subject, their data with caffeine and their data without caffeine, and then we can find the difference, placebo minus caffeine. And we see that most of our data points are positive, meaning that when they had their caffeine, they were on the placebo, they were less depressed than when the caffeine was taken away. So now we want to solve this problem. So first of all, why would researchers randomly assign the order in which subjects receive the placebo and caffeine? Researchers want to conclude that any statistically significant change in depression score is due to the treatment themselves and not some other variables. So one obvious concern is the order of the treatments. Suppose that caffeine was given to all subjects during the first 2-day period. What if the weather were nicer during these 2 days than during the second 2 days? That could affect the results. Researchers wouldn't be able to tell if there was a large increase in depression due to the caffeine or weather or some other type of event. There's always different like current events that could affect that as well. And so doing it randomly helps eliminate that as a reason. Okay. Next, if we want to actually carry out the problem, first we're going to state our hypothesis. Usually when we're using paired data, we would assume that the difference between the two sets of data would be 0. So we would say the mean difference would be 0. And then we would look at whether we think it makes more sense for the difference to be positive or negative based on how we did that difference, how we did the subtraction. So in this case, because we think that taking away their caffeine, that caffeine group, having that withdrawn, will potentially cause some depression. We think that the placebo group, who actually got their normal caffeine, will be more positive. So we think that the mean difference will be positive when we do placebo minus caffeine. This can be kind of tricky, and you sort of have to think about the situation to decide how we want to do this. Good idea to watch some extra example videos to help you with this. Okay, and then we choose an alpha value at the beginning before we move on. Okay, now we need to check our conditions. First, we can check off the random condition because we know that they were randomly assigned to the treatment groups and that good data procedures were followed. The 10% condition doesn't make sense when we're doing an experiment because we're not taking a sample. Our experiment is the whole population of the experiment, so it doesn't necessarily make sense to check that condition. We're going to skip it. The last condition that we would need to check is the normal/large samples condition. We don't know whether the actual distribution of the difference in depression scores is normal with such a small sample size. We need to examine the data so we can see some histograms and box plots and normal distribution plots. The histogram is irregular shaped with a few values. The box plot shows some right skewness but not a lot of outliers. And the normal probability is slightly curved, indicating some slight skewness, but with no outliers or strong skewness, we should probably be fine to continue with pretty good accuracy. So we do. Okay, so now we can use our calculator to find a p-value, which we get as 0.0027. So based on that p-value that we found with technology, we can say that it is safe to reject the null, that there's no difference between caffeine and no caffeine on depression, and we can say we have convincing evidence that the true mean difference, placebo minus caffeine, in depression score is positive for subjects like these. Basically, we need to be careful not to generalize too far outside of our experimental group. Okay, so another thing we need to consider is how large a sample do we need. Carrying out a significance test is often quite simple, especially if you use a calculator or a computer. Using tests wisely is not so simple, so here are some things we need to keep in mind. How large of a sample do we need? A smaller significance level requires stronger evidence to reject the null hypothesis. Higher power gives a better chance of detecting a difference when it really exists. At any significance level and desired power, detecting a small difference between the null hypothesis and alternative parameter values requires a large sample size. So basically, the choosing a level of significance and having good power of your test are kind of always butting up against each other, right? You don't want to reject the null when you shouldn't, and you shouldn't want to fail to reject the null when you shouldn't. So we have to balance those two things, and the easiest way to help us make better decisions is to have a larger sample, because that'll give our math, just basically allow it to be more accurate without having to make it more likely to make one mistake over another. Okay, last, statistical significance and practical importance. When the null hypothesis, or basically no difference, can be rejected at the usual levels of 0.05 or 0.01, there is a good evidence of a difference, but that difference may be very small. When large samples are available, tiny deviations from the null hypothesis will be significant. So basically, it can be proven to be statistically significant that there is a difference, but that difference itself might not be significant. It might be that there's a difference between the two groups of something super small that isn't actually that important. Is there a significant difference between these times? Well, it might be statistically significant that there is a difference, but it might be a difference of 1 second, and it actually doesn't really matter. So you got to be careful of that as well. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study to search for it, and use a significance test to weigh evidence you get. In other settings, significance tests may have little meaning. So it really is kind of significance tests really follow the scientific method. If you kind of use them willy-nilly, they might not mean the same thing in other contexts. So be careful. In general, you will learn more about specific testing approaches and methods that you might use in a specific field, kind of in courses in college specific to that field. So we'll talk really generally in this class, but you'll get more information as you actually get into a career path. That is it for our 9.3 video. If you would like more video examples, please look in the Schoology lesson.